In this video, we're going to take a look at how do we go through and use MATLAB to help us to be able to find the critical values of a function. Now, the critical values, you recall, are going to be those values to where we just take the derivative of the function, set it equal to 0, and then solve it. And then, of course, if the function is undefined at that point, that's another part of the critical values. And MATLAB is just going to help us to find these, but it's not going to find all of them. So we always have to go back and make sure that we fill in the blanks for the domain as well, the domain restriction of the derivative. So an easy way to do this is just to take the derivative of the function. So we, similar to the code that I have here, we just take a symbolic variable, define a function, in this case, x1 of x, and then we just find the derivative and then set that derivative equal to 0. And it's going to spit out what the solutions are to the critical values, okay, or to the equation that generates the critical values. Now, we can find the critical values over the real numbers or the given domain. Okay, so if I wanted to limit my domain to, let's say, -3 to +3, then I would just include some brackets in my solve function and then just define the bounds for this. Okay, so it says basically x has to be less than 3 but greater than -3. So let's take a look at a couple examples as to where we just use MATLAB to help us to find these critical values of these functions. So we're going to start with a nice easy polynomial over the real numbers. So we have 0.5x to the fourth minus x cubed minus x squared plus 2. So I'm going to go ahead and define my symbolic variable x. I'm going to define the function as 0.5 times x to the fourth minus x cubed minus x squared plus 2. Then we're going to find the derivative. I'm going to call that p. You can call it whatever you want. I'm just going to call it p, which is going to be the derivative of f with respect to x. And then finally, to find the critical values, we are going to solve the equation p double equals 0. All right, make sure you use 2 equals. Otherwise, it's going to assign p to be 0 as opposed to try to solve the equation. All right, so let's run this. And down here, it gives us our 3 critical values, which we should expect because when we take the derivative of f, it gives us a third order polynomial. So we should expect 3 solutions. All right, so pretty easy to do this. Now let's take a look at a second example. This time we're going to have a bound on our domain. So this time we're interested from 0 to 2 pi, and we have the function sine square x plus cos x. And if you're doing this analytically, this might be difficult for you to do to be able to find all of those, especially if you haven't been in depth with your trigonometry for a while. So MATLAB can kind of help you out with this. So let's start by defining our function. And I'm just going to reuse a lot of the same code. So we're going to have the sine of x squared plus cos of x. Right? And by the way, to define a trigonometric function to a power, make sure you put that trig function in parentheses and then raise it to a power. And then we're just going to have the same solve function, except inside, we're going to put a bracket beginning at p. We're going to say comma, and we're going to say x is less than or equal to 2 pi, comma, but x is greater than or equal to 0. And then we're going to close our bracket out, all right? And it doesn't matter if you do the less than or greater than first, all right? And I just decided that from the given problem, which was from 0 to 2 pi, all right? So let's execute this. And notice what it does is that it spits out all 5 of the critical values that would be generated. So that's pretty cool. And what would be really nice is if we could plot f. So we'll just do an easy plot. And we're going to see that these are or should be critical values in the given domain. All right, so we'll just run it and we see this. All right, and I guess I should limit the plot from 0 to 2 pi. Otherwise, it doesn't make a lot of sense. So let's go ahead and execute again, get a graph. All right, and so we can see right away that from 0 to 2 pi, we have a critical value here, and then we have one right about here, which is going to be, it looks like our pi thirds, if we put a grid on, and then we go all the way down here, and this is about 3.1, that's pi, and then we go back up, and this is going to be our 5 pi thirds, And then back down here is our 2 pi, which is going to be critical. If we were to expand the graph just a little bit, we'd be able to see that. So for instance, maybe we went to negative 0.5, and then instead of 2 pi, which is 6.28, we went to 7. We'll just execute this one last time. All right, we could see that we start to have those critical values around 0, because it's kind of that point of inflection. And then at 2 pi, 6.28, in this case, it gives us 6.255. But it looks like that those are our critical values of this function, which isn't necessarily an easy function to find those critical values for. So pretty cool that we can use MATLAB to help us find those functions, and then coinciding with the graph, it really shows us what those critical values mean. All right. So hopefully this has been helpful for you to understand how to utilize not just MATLAB to find critical values, but for a lot of the applications and sort of directives that we use the derivative for in calculus.